Okay, now that we have figured out how to identify forces on a force body diagram and how to find the net force, which gives us information about, which forces are winning out, so the direction things are going, let's start using that to identify if it's like an example of Newton's first law or an example of Newton's second law. So, for first law, the net force must be zero. And it can be in one direction, but usually both directions. Okay? So what that kind of means, how you can think about Newton's first law in this sense, an object in motion will stay in motion at the same speed and in the same direction unless a net force, that's that whole outside force, acts on it. Okay? So in order for Newton's first law to be what's happening, F net equals 0. So what that kind of means is that your normal force is equal to your gravitational force, and your frictional force is equal to your applied force. Okay, so if you ever see free body diagrams like this, that tells you your object is either at rest, all right, which means there's no applied force or frictional force. You just have a normal force and a gravitational force that are both 0. Or your object's moving at a constant speed. Talk about that. An object at rest, all right, if it's at rest, that means this is going to be 0. Your applied force will be 0, so therefore your friction will be 0. Okay? So your net forces will be 0. Another thing, if your object is at rest, it's probably sitting on a surface. So you're going to have an F sub g. Let's just pick a number. We're going to say F sub g is 5 newtons. That means your normal force also has to be 5 newtons. So that'll be 5 newtons plus negative 5 newtons, which equals 0. F net equals 0. Okay? So, this is one example where something is obeying Newton's first law. All of your forces cancel out to 0. In this case, we're at rest, so you actually have absolutely no applied force or frictional force. Second case of Newton's first law on a free body diagram is an object that's actually moving, but it's moving at a constant speed, which means no acceleration. Okay? What that means is, again, your net forces have to be 0. So if you have an applied force of 5 newtons, your frictional force also has to be 5 newtons. And say your gravitation is 12 newtons. That means that your normal force has to be 12 newtons. So here we have 5 plus negative 5 equals 0. And here we have 12 plus negative 12 equals 0. Okay? All right, so the two first law examples are an object at rest, so your normal force is equal to your gravitational force, your applied force and your frictional force are 0. Or you're moving at a constant speed. In this case, your two vertical forces are equal to each other, so normal force and gravitational force, same number. And your two horizontal forces, friction and applied, aren't equal to each other. Equal but opposite. So, second law, you can tell the second law is happening when you have a net force greater than 0. Okay? What this means is that you have acceleration. Okay? So, what's happening here is now we're not staying at the same speed, or we're not staying in the same direction. We have acceleration happening. All right, so we're speeding up, we're slowing down. The forces are unbalanced, so they aren't equal to 0. Okay, so what that means is one of the forces has to be greater than the other one. All right, so you might have an applied force that's greater than a frictional force, or maybe the force of gravity is greater, is greater than the normal force because you're falling and there's no normal force, okay? Things like that. So the of this that we'll see is an object that's falling. If you are falling, is there a surface underneath you? Hopefully you are saying no. That means that you have absolutely no normal force. No F sub n, which means whatever your gravitational force is, say it's 20 newtons, that wins, okay? And in this example, there could be applied forces and frictional forces, although typically if something's falling, it's usually falling straight down, so there's probably not any of those other forces, okay? So the big thing here is that you see 0 plus negative 20 equals negative 20 newtons in the y direction, all right? What your frictional force and applied force is irrelevant in this situation, all right? But big thing is we have a F net greater than 0. In this case, when I say greater than 0, I'm meaning it's non-zero, okay? The negative just implies the direction. Another example of Newton's second law is if you have an object accelerating horizontally, okay? That means that one, either F sub f or F sub a, is greater than the other one, okay? More often than not, we're going to talk about positive acceleration. So F sub a is, say that's 20 newtons, and your frictional force is 5 newtons. Your horizontal force is going to be positive 20 plus negative 5, which equals 15 newtons, okay? And again, in this case, the force of gravity and the normal force, they probably will cancel each other out, because typically, this is like in a car driving down the road. The car will have a gravitational force, and since it's on the surface a normal force, but the y F net ends up being 0. But as long as one of them, either in the x direction or the y direction, your net force is greater than 0, you have a second law example. So this will be 100 plus negative 100, which equals 0. But your F net, in this case, is greater than 0. You have 15 newtons, right? Okay. So at this point, I expect that not only could I give you a picture with forces labeled on it, but you should also be able to start labeling the forces. Okay, so for example, we have an FBD showing a 6 kilogram book at rest on a table. Draw all applicable forces. So if this book is at rest, that should indicate to you that there are 2 forces that we don't have. All right, if it's at rest and it's not moving, then we don't have any horizontal forces. Okay, so those are both 0. Now, to find the normal force and the gravitational force, I would say just get into the habit. Every single time you have a free body diagram, figure out F sub g, all right? F sub g is equal to mass times gravity. Our mass is 6 kilograms, all right? So mg, even though it doesn't say it, we always know that's 10 meters per second squared, so F sub g is going to be 6 times 10, or 60 newtons, all right? And then since this book is at rest, all right, that's an example of Newton's first law. So F net has to equal 0, which means our normal force has to be 60 newtons. Okay? Another example of this is draw an FBD showing Buffy pulling a 4 kilogram book horizontally across the table at a constant speed. The applied force is 20 newtons. Draw all applicable forces. So there's a few things in here. One, it tells us our applied force. So that one's easy. Let's just go ahead and label that one. All right, we can find our force of gravity since we have a mass. So m equals 4 kg. Gravity equals 10 meters per second squared. Our force of gravity, or weight, is equal to 4 times 10, or 40 newtons. Sorry, my equation there is mass times gravity. So we know that's 40 newtons, okay? And now, reading this, we are moving across the table at a constant speed. If you see the two words constant and speed right next to each other in a FBD problem, that implies Newton's first law, which means our F net has to be 0. So in order to make that 0, F sub A has to equal F sub F. So that's going to be 20 newtons. And F sub n has to equal F sub g, so that's going to be 40 newtons. And now our net force is 0. Okay? Now, last one is draw a free body diagram showing Buffy pulling a 5-kilogram book horizontally across the table with an acceleration of, and this didn't carry over my squared, but it's 2 meters per second squared. The frictional force is 0 newtons. So draw all applicable forces. Well, one, it tells us frictional force is 0, so we can go ahead and say that. But a couple of things, a couple of other numbers we have, these are going to help find other forces. So our F sub g is equal to mass times gravity. That's going to be 5 times 10, or 50 newtons. So there's 50 newtons. All right. There's also your applied force, since we are given an acceleration. F sub a is equal to mass times acceleration. All right. Any force technically is equal to mass times acceleration. You just have to know the acceleration. Okay. So in this case, we have a 5-kilogram book, and the problem tells us we're accelerating at 2 meters per second squared, so that's equal to 10 newtons. All right, and then the only one we don't have filled in right now is our normal force. That's the only one where you're never going to know the acceleration, because one, usually when you have a normal force, you don't have any acceleration in the vertical direction. And all it's doing is counteracting your force of gravity. So that is going to be 50 newtons. So your sum of your forces in the x direction are positive 10 plus 0. The sum of your forces in the y direction is positive 50 plus negative 50, which equals 0, and that equals 10. So our net force is in the x direction and is 10 newtons. Okay? So this is just, watch this video. If this doesn't make sense, watch it a few times. This is just my expectations of what you can do and determine from a free body diagram. All right? So make sure you know when it's Newton's first law, when it's Newton's second law. All right? These last 3 examples, this was a Newton's second law. The constant speed is Newton's first law, and the at rest was Newton's first law. But if you can do all of this, then you are golden. So make sure you do the online assignment and have notes in class tomorrow.